Okay, so let's begin. Welcome everybody to last talk of the day. It's by Manuel Ettengruber, and he's going to talk about search for fundamental scale of gravity. He's from the Institute of Theoretical Physics in Saclay, I think, France.
Yes, exactly. Close to
And
Paris.
yeah, okay. And let's begin. I'll send you a reminder when 5 minutes are left.
Thank you very much. Yeah, thank you also. I'm very honored for the invitation to speak here today to you. And my topic will be the big part of the research I did in the past years, namely the search for the fundamental scale of gravity. And what I mean with the fundamental scale of gravity is based on this result by Dwali, 2007, and Dwali and Redi, also in a follow-up paper. Namely, the fact that the fundamental scale of gravity, which I depict here with MF, is related to the Planck scale. And we have the following equation here, equation 1. And MP is here the Planck scale, and N is the number of particle species in your theory. And the fundamental scale is the scale where you expect that quantum gravity becomes strong. And this equation suggests as more particle species you have in your theory, the further this fundamental scale, so the scale where you actually expect quantum effects of gravity, depart from the actual scale where we originally expected, namely the Planck scale. And in the standard model, we usually have around 100 particle species, and therefore these are separated, but not so much separated. But there are other theories we will talk about where this separation can get stronger. And one argument how you can see this relation is when you imagine, also there are several arguments, let me just quickly go through one, is when you have a quantum field theory with n bosons with the mass lambda and exact discrete gauge symmetry written down here, the mass of the minimal black hole you can build with the maximum charge in it is just equation 2. And as soon this black hole will evaporate, or starts evaporating, and it reaches the temperature lambda again, then it can start emitting such bosons again. Because as long the temperature is smaller than the mass of the bosons, we know that then the evaporation of such particles is exponentially suppressed. And we know the mass when this will be the case, when it reaches the temperature of these particles, or the mass of these particles. And then we can calculate the maximum number of the emitted bosons by such a black hole. And you get this equation 3 here, where you already see relation 1. And this tells you the maximum mass the particles can have in your theory with n of these particles being present is lambda or mf. And you can also show that this is the scale where you expect black hole physics change. And you also can see that another argument is that the graviton propagator starts becoming non-perturbative at this scale mf, or exactly. And this tells you that you cannot neglect any quantum gravity effects anymore at this scale. So when we have this scale in nature, this fundamental scale, of course, there is the natural question, where do we expect this scale to be then? And this is the question of this talk. And here I wrote down energy line from low energies in the lower part and high energies up to the Planck scale in the upper end. And where would we expect something like this? And the original model which exploited this equation was the famous model of large extra dimensions, also called ADD model, where you have extra dimensions and you compactify them, and the resulting Kaluza-Klein modes are these extra species. And when you make the extra dimensions large enough, you can bring down this fundamental scale of gravity down to 10 TeV, and this would give you a solution to the hierarchy problem. And in a similar line, the many species theories are going, they also bring down the fundamental scale of gravity to this 10 TeV scale. And this is motivated by the hierarchy problem of particle physics. You can also go to the other end of the energy line and would say, okay, when we want to have real grand unification, so a unified theory where all forces we know in nature, like all the 3 gauge forces and gravity, should be unified, where would we expect then this fundamental scale, we could say it's 10 to the 16 GeV, and naturalness is one model that could explain such a fundamental scale. Or you have another scale that is motivated by the dark dimension, or another version of naturalness that is currently discussed in the literature, and where it puts it to 10 to 10 GeV. So this is just to summarize these models I mentioned, and all these models introduce many additional particle species, like the extra dimensional models with compactified extra dimensions are motivated with the n, so the number of particle species 10 to the 32, or the dark dimension version of this original ADD model that is currently discussed and introduces 10 to the 16 Kaluza-Klein modes. Many copies theories, where you have many additional copies of the standard model, also introduce 10 to the 32 species, and naturalness is either introducing 10 to the 4 or 10 to the 16. And okay, you have these models, so what is a smart way to search for the fundamental scale? Of course, the first intuition you would have is take collider experiments, because as soon as you start hitting this fundamental scale with your energy, you would expect quantum gravitational effects showing up in your collider experiments, like the production of gravitons. Of course, maybe not so intuitive are low energy experiments. We will talk about them in this talk, in particular neutrino experiments. Also, neutrinos would be sensitive to such new scale of gravity, and also astrophysical observations, in particular black holes, could show special signatures, special properties. And also about black holes we will talk in this talk. So let me start with neutrinos. And let me first introduce you to a mechanism for neutrino masses that is tightly related, but is where this additional species play a crucial role, because you can write down the Dirac operator here, which I did here in equation 4, and say, okay, when we have our neutrino of our standard model, let's depict it with L1, so the doublet L1, where our neutrino lives in, could mix with a lot of additional right-handed neutrinos. Imagine such a situation, and you have a bunch of new particles, like left-handed neutrinos and right-handed neutrinos, and you would write down this Dirac operator. And the crucial thing is here that you can exchange every right-handed neutrino with each other, because they are sterile under the standard model gauge group. And this means you can you basically have this matrix here, this Yukawa matrix, and from perturbativity of the theory, we know that in such a case, when you have a particle mixing with a bunch of other particles, the scaling of the Yukawa coupling should scale with 1 over the square root of n, where n is now the number of mixing partners for the neutrino. And therefore, I call this mechanism the many mixing partners mechanisms, because that's a general feature. As soon your neutrino mixes to many additional particles, your Yukawa coupling to these particles will be suppressed via equation 5. And this is then actually a natural explanation why the neutrino is light. The reason is because the Yukawa coupling has to be small. And when you now replace it with the equation 1 I showed you before, you can see also the suppression of the fundamental scale over the Planck scale, which would then be the solution to the neutrino mass problem. Let me say here, this n is not necessarily the n that goes into this equation 1, because the neutrino can mix with a different number of species than gravity does, because gravity, as we know, mixes couples to all particles, and the neutrino not necessarily. So they are tightly related to each other, but not totally the same, these two aspects. But an important point is here that such kind of neutrino mass models that exploit this many mixing partners mechanism is intrinsic infrared model. What I mean with that is the additional new states you introduce in such a scenario are not heavy, like what we have usually in CSILK type scenarios or radiative neutrino mass models, scotogenic model, where you always introduce a heavy new scale in your theory, and the new particles you introduce are heavy, and somehow this then suppresses the neutrino mass. This is what I call ultraviolet models. Infrared models, they don't need heavy new particles. They need, in this kind of theories, they need just additional light particles. They should be as light as the neutrino itself. So they would be searched at the electrovolt scale. And as I said, the theories I introduced before are using exactly this mechanism, and together with this gravitational anomaly mass generation suggestion, these models build this landscape of infrared neutrino mass models. And let me give you a specific example of the many species theories, where you say, okay, you have many additional copies of the standard model. This is the easiest model you can assume. What you have here is that you can actually write down the flavor state of our neutrino, here depicted with nu e. And what you see is that this flavor state you can write down in the mass basis, and the upper row of this equation is the standard model with neutrino masses part, let's say. So here the U are the usual PM&S matrix elements, M1, M2, M3 are the three mass eigenstates, and they get this prefactor square root n minus 1 over n. So, and additionally, you get this beyond standard model part, where you have these heavy mass eigenstates, which are related to the light ones via this equation here. So with this common mu, this mass factor, which relates the light mass eigenstate with the heavy mass eigenstate. And this mu is the same for all three of them. And the overall strength, or the overall contribution to the mass mass basis, goes with 1 over the square root of n. And this is already not surprising, because, as I said, the Yukawa coupling that sets the mixing is also scaling with 1 over the square root of n. So the contribution to the neutrino mass eigenstate, to the neutrino flavor eigenstate, also scales with 1 over the square root of n. What it tells you is that as larger the number of mixing partners for the neutrino goes, the smaller the effect will be. You see it here in this plot. The black line is the standard model oscillation pattern we would expect in the Dirac experiment. And when you have a small number of n, you see large deviations, and when you have a larger number of n, you see smaller deviations. And this is actually complementary. This tells us that neutrino experiments are complementary searches for this kind of effect to collider experiments, because collider experiments, they want large n's, a large number of particle species, because then the fundamental scale is very low, and you could hit it easier with collider experiments. You can easier reach these energies. Neutrino experiments are complementary to that, in the sense like you want to have small numbers in order to see something in neutrino experiments. And we use this to set bounds on these two new parameters we introduce in this model, namely the n and the mu. And we did a global neutrino fit with data from different neutrino experiments, namely the Diabay, Kamland, Minus, Nova, and the Katrin experiment. And the bounds we get, you see here in this picture. Here for the normal ordering, the mass factor is on the x-axis, the number of additional neutrino species on the y-axis. And we see here for the normal ordering, we can give a bound on the number of mixing partners for the neutrino up to 40, let's say, and which goes down when the mass factor is becoming very small. And in the inverted ordering, we can consistently give a bound on the number of neutrino species of 100. So another example I mentioned before was the naturalness proposal by these authors here. And what they do is they don't say they want to solve the hierarchy problem by bringing down the fundamental scale of gravity to TeV scale. What they say, imagine we have many realizations of our standard model, and the only thing that is changing is the Higgs mass parameter among these different models, different standard models. And then you have this interval of this Higgs mass parameters. And when you just introduce enough of them, it is natural that there exists a standard model realization where the Higgs is naturally small. And the idea is the same as if you would imagine an interval of 0 to 1, and you make one tick in this interval. What would be the average distance of this tick to one of the boundaries? It would be 1/2. If you would make 2 ticks into it, it would be 1/3, and so on and so forth. You just make enough ticks into this interval, and then the precision of a random pick is 1/n. And this would then explain why it would be natural to find a standard model solution, a standard model realization with a small Higgs mass. And the authors then give an example in their paper how you can have a natural cosmological model that naturally picks the lightest one, which we are living in. And this would then give a solution to the hierarchy problem. And now you can play the same game again. You have a situation where you have many additional mixing partners for your neutrino, which would automatically introduce the many mixing partners mechanism. Here, as I said, because of the structure in the Higgs sector with the Higgs mass parameter, you also have a structure in the WEF, of course. And this you use then to write down the Dirac operator. In the cosmological models they use, you can also induce a Weinberg operator in the form of 9 here. And you do the same game again. You write down your neutrino interaction state in the mass eigenstate at mass basis. And a very interesting feature of this model is that the Dirac case and the Majorana case have a different scaling in the delta m squared, so the mass differences among the different mass eigenstates, which is very peculiar because usually you cannot distinguish in neutrino oscillation experiments Majorana neutrinos from Dirac neutrinos. This is not the case if a naturalness is realized. There you would definitely see a difference in the Dirac case and the Majorana case. And it would look like the following. You see here the Dirac case in the Dirac experiment. Here you see again this n in the effect of the n, namely that with small n you have larger deviations, with larger n you have smaller deviations from the standard model depicted here in blue. And this would be the same plot for the Majorana case, and you see here you have a clear distinction in the observable neutrino oscillation pattern for the naturalness case. And last but not least, let me come back to extra dimensional mods, which were the first example for this kind of neutrino mass generation. What you have there is you have, additionally to your 4 dimensions we are living on, you have extra dimensions, and these extra dimensions, because we don't see them, they are compactified on a circle, for example. And we are living on a 4-dimensional brane. So standard model particles are living on the 4-dimensional brane, but particles that are not charged under the standard model, like the graviton or a stereo neutrino, can propagate into the whole space that is available, which is called the bulk. And then you would have, when you have compactification of extra dimensions, you have these Kaluza-Klein mass towers, which give you such scaling here. With what we did here is we also introduced a bulk mass for our bulk neutrino field, so the right-handed neutrino field. And then you can play the same game again, and you see the deviations from the standard model here. And we gave then bounds to the ADD model here, but we also gave bounds to the dark dimension version of the ADD model, which is currently discussed by swampland conjectures, where they say where they introduce this 10 to the 10 GeV mass scale in their theory to solve the cosmological constant problem instead of the hierarchy problem, actually. And of course, you can have the same solution to the neutrino mass problem, this kind of approach. But in order to have the dark dimension be realized, we need a small hierarchy for this bulk mass parameter we introduced to satisfy the constraints neutrino oscillation experiments give you. So you see here, when you have a positive bulk mass, you tighten actually the constraints. And the striking feature of the dark dimension proposal is that they say we know the size of the extra dimension should be 10 to the minus 1 or 10 micrometer. So this is the ballpark they are looking at. And neutrino oscillation experiments are already very tight to rule this kind of size out. So we can basically rule out in our results that a positive bulk mass, but when you have a negative sign here, you see the bound loses its strength, and you can get rid of the bounds in such a case. So these are neutrinos which can be used to search for such effects. Also, black holes are natural laboratories to search for the fundamental scale. And the reason for this is, okay, when you have this new scale, we know that heavy black holes, astrophysical black holes, they are fully Einsteinian black holes. So these follow the general relativity as we know. But with this new scale in the game, the fundamental scale, when you have a black hole that is as heavy as the fundamental scale, this object would be a fully quantum object. This means that you have a transition period from an Einsteinian black hole to this quantum black hole. And this intermediate regime can be quantified, given by these papers here. In the extra dimensional picture, this is a natural geometrical interpretation. That means as soon the black hole becomes smaller than the size of the extra dimension, it would become a higher dimensional black hole and not a four-dimensional one anymore. And then the properties of black holes changes, the Schwarzschild radius changes, accordingly also the entropy for black hole in the extra dimensional theory would change, or in the species part they would change. And what you see here is this enhancement factor. So the n, which is a large number as we argued, enhances the entropy compared to the four-dimensional case. And similarly, in the extra dimensional model, where the r is the size of the extra dimension and rs is the four-dimensional Schwarzschild radius, and as soon this rs becomes smaller than the extra dimension, you see here this is a number larger than 1 and would give an enhancement to the entropy of the black hole. Why I'm mentioning this is because in black hole physics currently discussed is the so-called memory burden effect that says the black hole should start slowing down after a specific point in time with its evaporation due to the information load that is bottled into the black hole. And the latest time would be page time, so when the black hole loses half of its mass. But in general, this effect, this memory burden effect, can kick in much earlier, and the evaporation rate is given by equation 23 here. So this is the semi-classical Hawking evaporation rate, which we usually know. And the black hole, the memory burden effect suggests that you get an additional suppression by 1 over the entropy to the power k, where k is a model parameter. And this would give you then the evaporation rate in the memory burden phase. And theoretical studies suggest that these two parameters which are of interest for this transition between the semi-classical phase and the memory burden phase, Q, where Q is the fraction of the mass that the black hole loses when it's until it's entering the memory burden phase, and delta, which is showing the width of this transition phase. And then you can do this because we know the entropy expressions in the extra dimension and in the species case. You can calculate these parameters which are of interest for the memory burden effect, the Q and the delta accordingly. And what we find is that the memory burden effect, so the slowing down of the evaporation after a specific point in time of the black hole, is stronger, sets in earlier, and with a sharper transition in the extra dimensional or in the species case. And this has interesting effects, of course, for the question what would be a window for primordial black holes and of evaporation behavior of black holes in general. And we find, let me just point out here one very nice result we found, is that In the most extreme case, in the extra dimensional case of ADD, which with the fundamental scale being around 10 TeV, that black holes with a mass 10 to the minus 10 grams, this is 5 orders of magnitude below the Planck scale, could still have lifetime of the universe. And yeah, this would make them then black hole dark matter candidates. But you don't need these micro black holes, this special kind of black holes, to be dark matter, but they can also be produced in astrophysical sources like active galactic nuclei, because these environments can accelerate particles to very high energies, to up to over 10 to the 8 GeV. And as soon as you have processes that are having a scattering beyond the fundamental scale of gravity, you expect that the black hole is formed. And the production cross-section is scaling with the geometric cross-section of such black holes. And this would mean in an AGN, so a supermassive black hole surrounded by a corona that accelerates particles, would also produce micro black holes in its corona. And there are 3 effects that can actually seen in such a situation. First, these jets, these AGNs usually have, should be cooled by such a process, by this black hole production process. And this would mean that if this cooling is faster than the standard model cooling, which we usually expect, then you can give a bound to the fundamental scale of gravity. And we did this by just demanding that the effect should not be larger than the standard model effect. Otherwise, we would have seen it already, that the most conservative bound we can get is 0.3 TeV to the fundamental scale by AGN cooling. But these bounds can get stronger depending on what we will find out in the future about AGNs, because we don't understand them very well. And for example, if the KM3 net event seen is by such a source, by such an AGN, you can already raise the bound up to almost 10 TeV. And for example, when you see ever GZK neutrino with such an energy scale, you can go over the 10 TeV limit and so on and so forth. And the most, when you push astrophysics to its boundaries, you can maybe go even to the PeV level, how you can give bounds to such models in such a case. But of course, you could also search for the Hawking evaporation spectrum in the spectrum of such AGNs. So here you see the black body radiation of such micro black holes in the corona of such an AGN. And you see, as higher the fundamental scale gets, as smaller the amplitude of the energy of the particle flux is that we would expect from such AGNs. But of course, they are hidden in the actual net standard model-like spectrum that is actually also produced by the AGN. And last but not least, there could be also a funny signature in a brain world scenario, extra dimensional scenario, where you have additional brains located in your extra dimension, and we would live on one of these brains. An AGN could accrete these brains to itself, and the corona of the AGN doesn't have to be on our brain. It could be in this dark brain, which we don't see. So the particles that accelerated by the AGN are not our particles. They would be living on another brain, but they could produce particles that could travel to us, like a graviton. As I said, in an extra-dimensional model, gravitons can travel to our brain and could decay here to particles that we could observe. So, for example, a photon. And this would mean we can have a point in space, and we can see it with our telescopes, where we would actually see nothing. Like, it could be in a total void. There is no corona, there are no particles around, but it could still be a source of highly energetic particles. And this would be a very clear signature for such a brain world scenario. So let me come to my conclusions. In low-scale gravity theories, we have plenty of observables for low-energy experiments and distinctive signatures in astrophysical searches. The many mixing partner mechanism that is motivated or realized in such models is an alternative to the neutrino mass problem. Neutrinos and neutrons, also, I didn't talk about them here, natural candidates for search for such oscillation spectrum. And the oscillatory behavior is very distinctive and predictive in such theories because of their low number of additional parameters. And also black holes are nice laboratories to search for the effects of the fundamental scale. And particularly the memory burden effect could be shifted to be stronger, sets in earlier and with sharper transition. 10 to the 10 gram heavy black holes could still have the lifetime of our universe. And AGNs are laboratories where we can also search for observables of such kind of theories. So that's it, and thank you for your attention.
Thank you for the nice talk. Any question from the audience, please?